Well, welcome to the first of several um, biology mathematics videos. Um, this is meant mostly for AP biology students, but maybe other students would find these videos to be helpful in some way. We're going to start talking about something called a chi-square test. And before we go too far into it, we'll just say that the chi-square test is a great tool to use to kind of navigate your way around problems where you might suspect that something has gone wrong, that maybe what you've assumed about a problem is no longer correct. So let's let's put it right into practice right away so you can kind of get a sense of what we're talking about here. Um, so simple and really common kind of probability exercise is to think about, what would happen if you rolled a six-sided die a certain number of times, and what are your expectations around the outcomes? And so, we could think about rolling a six-sided die 60 times, and of course, our expectation is that each side, each face would show up about 10 times. In fact, we would predict 10. But it's probably likely that if a particular side came up 11 times, like if there were 11 sixes or nine sixes, you wouldn't be too alarmed. You'd think, well, that's going to happen. It's pretty close to 10, and 11 and 9 are close. So yeah, there's nothing to think about here. We're still believing that our assumptions about the die are correct, that each side is equally likely to show up. But you, of course, would feel really differently about this if 60 sixes came up. You would truly suspect, and more than suspect, you would be absolutely convinced that the die were somehow faulty. Okay, so somewhere between 10 times and 60, you would start to think that the die was somehow faulty, that our assumption of equally likely outcomes for each of the six sides was unjustified, that it made sense before the test, but after the test, uh, it can't quite be true. So what do? We do something called a chi-square test, and it's a wonderful tool for kind of checking to see whether our expectations about an event are valid or not. So let's take a look at how this chi-square test gets implemented. Here is, I'm going to just do little yeah, shading here. Here's a sample experiment where we use the chi-square test, and we're going to roll a six-sided die 60 times. And so these are the expectations. Okay, we'll just kind of reveal a little bit at a time here. Those are the six possible outcomes, and of course, we would expect each of them to show up, or to roll out 10 times. And so now what happens if we get this as our set of observations? So that seems like an outcome that, I don't know, in my gut seems like that's not too odd, although there's only one outcome here that is exactly 10. The others seem pretty close, and I don't necessarily have any concerns about this, but that's the exact point of the chi-square test, which is to kind of determine with some sense of precision whether or not we need to abandon our sense of what or to change our assumptions about the problem. Okay, so let's look at the calculation that gets done. We're going to be looking at observations and expectations, and there is a little formula, okay, that we're going to use multiple times here. Okay, it'll be the observed minus the expected value. And that'll be a difference. We'll square that difference and then divide by the expected value. Okay, so we're going to get a series of numbers here that just allow us to start to characterize the difference between what we observe and what we expect. And one would think that, if this was a large number, that would be unusual. If it's a small number, it's not so worrisome. So let's do the first one here, okay? Um, For face number one, for having a 1 show up, we expected 10, we observed 11. So observed minus expected is 11 minus 10, which is 1. 1 squared is 1, and 1 divided by 10 is 0.1. All right. And we could do the same thing for the 2's. 12 minus 10 is 2. 2 squared is 4. 4 divided by 10 is 0.4, and so on and so forth. We get a similar value, of course, for the 3's and the 4's. And notice that there's some wisdom here. Squaring the result means that whether you're above or below, like we have in the 2's and the 3's, you still get a 0.4. It's just really about differences, right? This is why the number is called a chi-squared number. All the differences are squared. We get a 0 for the 5, and then our largest error is with the 6, and that turns out to be, a difference of 3 squared makes it 9. 9 divided by 10 is 0.9. So those are the individual pieces of what will eventually be our chi-squared calculation. So let's reveal the whole thing here. All right. Oops. What is that? There we go. The chi-squared value is the sum of all those squared differences divided by the expectations, okay? So just add up all these numbers, 0.1, 0.4, 0.4, 0.4, 0, and 0.9. If I've done my math right, I should get a chi-squared number of 2.2. Let's just quickly check. 0.1 plus 0.4 is 0.5, and another 0.9, and another 1.3, and 0.9 will give us 2.2. I think I got it right. Okay, let's pause just for a second. Okay, so we have a number. Our chi-squared number for this experiment is 2.2, but it's fair to ask, what does that mean? Is it a big number? Is it small? What context is this in? And how does it help us decide if the die is a fair one or not? Okay, so there is something called a chi-squared table, and this is a really familiar table that is provided to all AP biology students. Okay. And the chi-squared table is a series of numbers, and it's organized in a certain way. Each column, 1 through 8 here, is arranged by what we call a degree of freedom. We'll talk about that in a moment. And each row is labeled by a probability. And this is a probability, in this case, say 5% here or 1% there. The probability that the results are due simply to random variation. So that if you have a number in this row here, you're talking about that there's a 5% chance that the results were due to just simply random variation. So that's the chi-square table, okay? But what do we do with that? Well, okay, this is a little bit involved, but let's walk through it, okay? First of all, if the chi-square number is smaller than a critical value from the table, a little typo there, let me change that, okay? If the chi-squared value is smaller than a critical value in the table, then we say that there's not enough evidence to rethink our assumptions. Like in our case, we would say there's no reason to doubt that the sides are equally likely. But if it's larger, okay, if it's larger than the critical value, and we'll figure out what that critical value is in a second, if it's larger, then we say that we are 95% confident if we're in the first row here, or 99% confident that the results are inconsistent with our assumptions, that our assumptions are quite likely not correct, okay? So we're just trying to sort of confirm whether or not our assumptions make sense or not, okay? So let's dig in a little deeper here and go to this next page here and talk about the degrees of freedom and then using what's our critical value, okay? The degrees of freedom is pretty simple. It's always one less than the number of outcomes that are possible. We had 6 outcomes, 1 through 6, so there are 5 degrees of freedom. So we look here in this column marked 5 degrees of freedom, okay? Is 2.2 larger than either number? Well, clearly it's not. It's smaller than 11.7, it's smaller than 15.9, and so there's not enough evidence to suggest the results are anything other than random variation, okay? That the assumption that the sides are equally likely is still valid. Um, this is in statistics and AP biology, another way of saying that is that we accept the null hypothesis. It's a very specialized language that just means that there's nothing out of the ordinary here, that the results are really just due to random chance. Okay. Um, but what if, for example, the number had come out to be 12? Okay. If our chi-squared number turned out to be 12, here's what we would say. It's obviously larger than 11.07, so it beats that number there, but it's not larger than 15.09. So then we would say that there's a 95% chance, that's 1 minus 0.05, 95% chance that these results are inconsistent with our assumption that the faces are all equally likely, okay? Um, if the number was larger than 15.1, we would say the same thing, but with 95% confidence. Another way of saying that is that we would reject the null hypothesis and suspect that something else other than what we were assuming was correct. Okay. So there's a lot there, and it's well worth trying other problems, and it's well worth going to, say, this page here and just playing around with these numbers here, like make it 15 and 5 and 15 and 5 and 15 and 5, and see what your results would be. Okay, but I'll leave that for an exercise for you to try, and we're going to be applying the chi-square test in a couple of other videos. So we'll see this calculation happen a few times. Okay, hope that was helpful. Take care.